Alright, am I online? Let's check it, make sure everything is working well. I'm excited for this. This is going to be a long stream, but it's going to be a stream very worth it from what I've heard about this topic. So, alright, looks like everything's working. Let's just get right into it. Chapter 12, Matrix Groups and Symmetry. When Felix Klein, born in 1849 and died in 1925, accepted a chair at the University of Erlangen, he outlined in his inaugural address a program to classify different geometries. Central to Klein's program was the theory of groups. He considered geometry to be the study of properties that are left invariant under transformation groups. Groups, especially matrix groups, have now become important in the study of symmetry and have found applications in such disciplines as chemistry and physics. In the first part of this chapter, we will examine some of the classical matrix groups, such as the general linear group, the special linear group, and the orthogonal group. We will then use these matrix groups to investigate some of the kind of ideas behind geometric symmetry. 12.1 Matrix Groups. Some facts from linear algebra. Before we study matrix groups, we must recall some basic facts from linear algebra. One of the most fundamental ideas of linear algebra is that of a linear transformation. A linear transformation, or linear map, T from R to the n to R to the m, is a map that preserves vector addition and scalar multiplication. That is, for vectors x and y in R to the n, and a scalar a and r, we have t of x plus y is equal to t of x plus t of y, and t of ay equals a t of y. An n by n matrix with entries in R represents the linear transformation from R to the n to R to the m. If we write vectors x equals x1 all the way to xn transpose, which I'm just going to put this notation here, x1, x2, all the way to xn transpose is equal to the column vector x1, x2, all the way to xn. So, we write vectors x equals x1 all the way up to xn transpose, and y equals y1 all the way up to yn transpose in order to the n as column matrices. Then an n by n matrix, A equals A11, A12, all the way to A1n, and likewise down up to the row AM1, maps the vectors to Rm linearly by matrix multiplication. Observe that if alpha is a real number, Ax plus y equals Ax plus Ay, and alpha Ax equals A alpha x, where x is the column vector x1, x2, all the way to xn. And with this convention, we often also abbreviate the matrix A by writing A sub ij, and this determining the entire matrix, because you would know the rule for determining the aij. Conversely, if T from R to the n to R to the m is a linear map, we can associate a matrix A with T by considering what T does to the vectors E1 equals 1, 0, all the way continuing with 0 as T, E2 is equal to 0, 1, 0, 0, on to 0, T, and roughly EI being the ith basis vector, or the vector with a 1 in the ith place and 0s everywhere else. We can write any vector x equals x1 all the way up to xn transpose as x1 e1 plus x2 e2 all the way to plus xn en. Consequently, if t of e1 is equal to a11, a21 all the way to am1, te2 is equal to a12, a22 all the way to am2, on and on to ten is equal to a1n, a2n all the way to amn, then tx is equal to t of x1 e1 plus x2 e2 plus xn en. Then using linearity, we can break it up to have it become x1 te1 plus x2 te2 plus xl all the way up to xn ten, which is equal to the sum from k equals 1 to n of a1k xk, on and on all the way up to the sum from k equals 1 to n of amk xk is equal to ax. If we let t be t from r squared to r squared be the map given by t of x1, x2 equals tx1 plus 5x2, negative 4x1 plus 3x2, the axioms that t must satisfy a linear transformation are easily verified. The column vectors t e1 equals 2, negative 4 transpose, and t e2 equals 5, 3 transpose tell us that t is given by the matrix A equals 2, 5, negative 4, 3. Since we are interested in groups of matrices, we need to know which matrices have multiplicative inverses. Recall that an n by n matrix A is invertible exactly when there exists another matrix A to the negative 1, such that a negative 1 equals a negative 1a equals I, where I is equal to 1, the identity matrix, or the matrix with 1s all the way down the diagonal, is the n by n identity matrix. From linear algebra, we're assuming you've taken linear algebra, we know that A is invertible if and only if the determinant of A is non-zero. Sometimes an invertible matrix is said to be non-singular. Example 12.2. If A is the matrix 2, 1, 5, 3, then the inverse of A is A to the negative 1 equals 3, negative 1, negative 5, 2. We are guaranteed that A to the negative 1 exists, since the determinant of A is equal to 2 times 3 minus 5 times 1 equals 1 is non-zero. Some other facts about determinants will also prove useful in the course of this chapter. Let A and B be n by n matrices. From linear algebra, we have the following properties of determinants. First, we've actually proven this in the case of 2 by 2 matrices. The determinant is a homomorphism into the multiplicative group of real numbers. That is, the determinant of A times B is equal to the determinant of A times the determinant of B. If A is an invertible matrix, then the determinant A to the negative 1 is equal to 1 over the determinant of A. If we define the transpose of a matrix A equals A sub ij to be A to the t equals AJI, then the determinant of A transpose is equal to the determinant of A. Let T be the linear transformation associated with an n by n matrix A. Then T multiplies volumes by a factor of the absolute value of the determinant of A. In the case of R squared, this means that T multiplies areas by the absolute value of the determinant of A. Linear maps, matrices, and determinants are covered in any elementary linear algebra text. However, if you have not had a course in linear algebra, it is a straightforward process to verify these properties directly for 2 by 2 matrices, the case which we were most concerned. The general and special linear groups. The set of all n by n invertible matrices form a group called the general linear group. We will denote this group by GLN R. The general linear group has several important subgroups. The multiplicative properties of the determinant imply that the set of matrices with determinant 1 is a subgroup of the general linear group. See the last chapter and the first isomorphism theorem. Or not first isomorphism theorem, the theorem of the kernel of a homomorphism is itself a normal subgroup. Stated another way, suppose that the determinant of A is equal to 1, and determinant of B is equal to 1. Then the determinant of AB is equal to the determinant of A, determinant of B is equal to 1, and determinant of A to the negative 1 equals 1 over determinant of A is equal to 1. This subgroup is called the special linear group, and is denoted by SLN of R. Example 12.3. Given a 2 by 2 matrix A equals ABCD, the determinant of A is AD minus BC. The group GL2R consists of those matrices in which AD minus BC is not equal to 0. The inverse of A is A to the negative 1 equals 1 over AD minus BC times D negative B negative CA. If A is an SL2R, then A to the negative 1 equals D negative B negative CA. Geometrically, SL2R is the group that preserves the areas of parallelograms. Let A be equal to 1, 1, 0, 1, be an SL2R. In figure 12.4, the unit square column corresponding to the vectors x equals 1, 0 transpose and y equals 0, 1 transpose is taken by A to be the parallelogram with sides 1, 0 transpose and 1, 1 transpose. That is, AX equals 1, 0 transpose and AY is equal to 1, 1 transpose. Notice that these two parallelograms have the same area. So you can think of it as this unit square being moved by this transformation right here to be that shear transformation. But because the determinant equals 1, we know that these shapes actually already have the same area. And specifically, you can think of this as SL2R acting on the unit square. Acting being a later technical term that we'll define for group actions. The orthogonal group O of n. Another subgroup of GLNR is the orthogonal group. A matrix A is orthogonal if A to the negative 1 is equal to A transposed. The orthogonal group consists of all sets of orthogonal matrices. We write O of n for the n by n orthogonal group. We leave as an exercise the proof that On is a subgroup of GLNR. So we'll get to it when we get there. Example 12.5. The following matrices are orthogonal. 3/5, negative 4, 5, 4/5, 3/5, 1, 2, negative 3 over square root of 3 over 2, square root of 3 over 2, 1, 2, and these. There's a way of doing this which is much easier and illuminates why, how you would generate these really weird examples. involves sine and cosine, but I'm going to just leave it at that for now, and we'll get more specifically into that later. There is a more geometric way of viewing the group On. The orthogonal matrices are exactly those matrices that preserve the length of vectors. We can define the length of a vector using the Euclidean inner product, or dot product, of two vectors. The Euclidean inner product of two vectors x equals x1 all the way to xn transpose, and y equals y1 all the way to yn transpose, is, I'll call this the dot product between x and y, but you would strictly read it off as Langle x, y wrangle, is equal to x transpose y, equals x1, x2 all the way to xn, times y1, y2 all the way to yn, is equal to x1, y1 plus x2, y2, plus on and on, 2 plus xn, yn. We can define the length of a vector x equals x1 all the way to xn transpose to be the absolute value of x is equal to the square root of the product of x with itself equals the square root of x1 squared plus x2 squared all the way to plus xn squared. Associated with the notion of length of a vector is the idea of distance between two vectors. We define the distance between two vectors x and y to be the length of x minus y. We leave as an exercise the proof of the following propositions about the properties of the Euclidean inner product. Proposition 12.6. Let x, y, and w be vectors in Rn and alpha in R. Then xy is equal to yx, y plus w is equal to xy plus xw, axy is equal to xay is equal to axy, xx is greater than or equal to 0 with equality exactly when x is equal to 0, and if xy is equal to 0 for all x in Rn, then y is equal to 0. This is going to be something where I'll prove some of these, but a lot of these you cover when you're talking about metrics and you're talking about norms, either in the context of topological spaces, mainly with metric spaces, or you're talking about Hilbert spaces. So I'll cover some of these, but not in too much detail. Example 12.7. The vector x equals 3, 4 transpose has length square root of 3 squared plus 4 squared equals 5. We can also see that the orthogonal matrix A equals 3, 5, 4, 5, negative 4, 5, 3, 5 preserves the length of this vector. The vector ax equals negative 7 over 5, 24 over 5 transpose also has length 5. Since determinant of A transpose is equal to determinant of I is equal to 1, and determinant of A is equal to determinant of A transpose, the determinant of any orthogonal matrix is either 1 or negative 1. Consider the column vectors aj is equal to a1j, a2j, all the way up to anj of the orthogonal matrix A equals aij. Since A transpose equals I, AR AS is equal to delta RS, where ARS is equal to 1 if R is equal to S, or 0 if R is not equal to S. And we call delta RS the Kronecker delta. Accordingly, column vectors of an orthogonal matrix all have length 1, and the Euclidean inner product of the distinct column vectors is 0. Any set of vectors satisfying these properties is called an orthonormal set. Conversely, given an n by n matrix A, whose columns form an orthonormal set, it follows that A to the negative 1 is equal to A transposed. We say that a matrix A is distance preserving, length preserving, or inner product preserving when the length of AX minus AY is equal to the length of X minus Y, the length of AX is equal to length of X, or the inner product of AX and AY is equal to the inner product of X and Y respectively. The following theorem, which characterizes the orthogonal group, says that these notions are all the same. Theorem 12.8. Let A be an n by n matrix. The following statements are equivalent. 1. The columns of the matrix A form an orthonormal set. 2. A to the negative 1 is equal to A to the A transpose. 3. For any vectors x and y, AX, AY, and their inner product is the same as the inner product of x and y. 4. For vectors x and y, the length of ax minus ay is the same as the length of x minus y. And 5. For any vector x, the length of ax is equal to the length of x. Proof. We've already shown 1 and 2 to be equivalent. 2 implies 3. The inner product of ax and ay is equal to ax transpose dot ay is equal to x transpose a of y is equal to, since we're working with orthogonal matrices, is equal to xt of y is equal to the inner product of x and y. 3 implies 2. Since xx equals ax equals x transpose at ax is equal to x at ax, we know that x ata minus ix equals 0 for all x. Therefore, ata minus I is equal to 0, where a to the negative 1 equals at. And this comes from later things we'll prove about the inner product. 3 implies 4. If a is inner product preserving, then a is distance preserving, since the length of ax minus ay squared is equal to the length of ax minus y squared is equal to the dot product of ax minus y and ax minus y is equal to the dot product of x minus y is equal to the length of x minus y squared. 4 implies 5. If a is distance preserving, then a is length preserving. Letting y equal 0, we have the length of ax is equal to the length of ax minus ay is equal to the length of ax, is the length of x minus y is equal to the length of x. 5 implies 3. The final implication in this amazingly long loop of implications. We use the following identity to show that length preserving implies inner product preserving. The inner product of x and y is equal to 1/2 times the inner product of x plus y squared minus the inner product of x squared minus the inner product of y squared, or the length of x plus y squared minus the length of x squared minus the length of y squared. Observe that ax ay is equal to 1/2 ax plus ay squared minus the length of ax squared minus the length of ay squared is equal to, using linearity, 1/2 the length of ax plus y squared minus ax squared minus ay squared is equal to 1/2, using the length preserving property, 1/2 of the length of x plus y squared minus the length of x squared minus the length of y squared is equal to the inner product of x and y. That was a long one. But we have shown the equivalence between all these different geometric intuitions, and you use all of them at different times, so it is important to become somewhat familiar with these. Alright. Figure 19, 12.19. This shows that O of 2, it shows O of 2 acting on R squared. In this case, we'll see a thing of A and B being turned to sine of theta, cosine of theta. And generally, you already have a bit of a hint here about how these matrices might work, but. Example 12.10. Let us examine the orthogonal group on R squared a bit more closely. An element A in O of 2 is determined by its action on E1, 1, 0 transpose, and E2, 0, 1 transpose. If AE1 equals AB transpose, then A squared plus B squared is equal to 1, since the length of any vector must be preserved when it is multiplied by A. Since multiplication by an element of O2 preserves length and orthogonality, AE2 equals plus or minus negative B A transpose. If we choose AE2 is equal to negative BA transpose, then A is equal to A negative B, BA, is equal to, for some theta, cosine of theta, negative sine of theta, cosine of theta, where 0 is less than or equal to theta is less than 2 pi. The matrix A rotates a vector in R squared counterclockwise about the origin by an angle of theta. If we choose AE2 equals B negative A transpose, we then obtain the matrix B equals A B, B to the negative A, equals cosine of theta, sine of theta, negative cosine of theta. Here, the determinant of B equals negative 1, and B squared is equal to 1, 0, 0, 1. A reflection about the horizontal axis is given by the matrix C equals 1, 0, 0, negative 1, and B is equal to AC. Thus, a reflection about a line L is simply a reflection about the horizontal axis followed by a rotation. Two of the other matrix or matrix-related groups that we will consider are the special orthogonal group and the group of Euclidean motions. The special orthogonal group, SON, is just the intersection of O of n and SLN of R. That is, those elements O and ON with determinant 1, because notice we had some elements in O of n with determinant negative 1. It was never anything like greater than, or like, it was never anything different from 1 or negative 1, but it could be either of them, and this is just cutting that out. The Euclidean group, En, can be written as ordered pairs AX, where A is in O of n, and x is an r to the n. We define matrix multiplication by ax by is equal to ab ay plus x. The identity of this group is I0. The inverse of ax is an a to the negative 1, negative a to the negative 1x. In exercise 12.4.6, you are asked to check that En is indeed a group under this operation. And this basically can roughly define the reason we don't have it be ay and bx is that the Euclidean group allows for rigid motions and translations and things like that. The Euclidean group is more general and doesn't require that we have things fixed. Symmetry. An isometry or rigid motion in r to the n is a distance-preserving function f from r to n to rn. This means that f must satisfy the length of f of x minus f of y is equal to the length of x minus y for all x and y in Rn. It is not difficult to show that f must be a one-to-one map. By theorem 12.8, any element in On is an isometry on r to the n. However, On does not include all possible isometries on r to the n. Translations by a vector x, ty of x is equal to x plus y, is also an isometry, as we can see in figure 12.11. So this shifting up here. However, T cannot be an On, since it is not a linear map. We are mostly interested in isometries in R squared. In fact, the only isometries in R squared are rotations and reflections about the origin, translations, and combinations of the two. For example, a glide reflection is a translation followed by a reflection. In R to the n, all isometries are given in the same manner. The proof is very easy to generalize. Working up to it, it is a bit, but it is a fair amount to actually describe. But what we're going to be doing here is just going to be first building up a lemma to help us prove that. So, lemma 12.13. An isometry f that fixes the origin in R squared is a linear transformation. In particular, f is given by an element in O of 2. Proof. Let f be an isometry in R squared fixing the origin. We will first show that f preserves inner products. Since f of 0 is equal to 0, the length of f of x is equal to the length of x. Therefore, the length of x squared minus 2 times the inner product of f of x and f of y plus the length of y squared is equal to the length of f of x squared minus 2 times the inner product of f of x and f of y plus the length of f of y squared is equal to f of x minus f of x minus f of y, the inner product of that, is equal to the inner product of f of x minus f of y squared, is equal to the length of x minus y squared, is equal to x minus y, the inner product of x minus y and x minus y, which is equal to the inner product of x squared minus 2xy plus y squared. Consequently, the inner product of f of x, f of y is equal to the inner product of x and y. Now, let E1 and E2 be in 1, 0, be 1, 0, 2 transpose and 0, 1 transpose respectively. If x is equal to x1, x2 is equal to x1 E1 plus x2 E2, then f of x is equal to f of x, f of E1 times f of E1 plus the length, the inner product of f of x, f of E2 times f of E2 equals x1, f of E1 plus x2, f of E2, from which the linearity of f easily follows. For any arbitrary isometry, f tx of f will fix the origin for some vector x in R squared. Reminder here that this notation means we shift it to x. So let me quick write down the notation they're using. So if t from r to the n to r to the m linear, r to the m is linear, then we have tx is defined to be t minus x, or t plus minus x. All that really matters is that we choose some notational convention that's accurate. In this case, we're going to say t plus x. Tx of y is going to be defined to be t of y plus x. Hence, tx of fy is equal to ay for some matrix A in O2. Consequently, f of y is equal to ay plus x. Let me reread this. For any arbitrary isometry f, txf will fix the origin for some vector x in R2. Hence, tx of fy is equal to ay for some matrix A in O2. Consequently, f of y is equal to ay plus x. Given the isometries, f of y is equal to ay plus x1, and g of y equals by plus x2, their composition is f of g of y equals f of by plus x2 equals aby plus ax2 plus x1. This last computation allows us to identify the group of isometries on R squared with E of 2. Theorem 12.14. The group of isometries on R squared is the Euclidean group E2. Notice that this right here, because x1, x2 are fixed in place, is exactly what we were talking about previously. Alright. A symmetry group in Rn is a subgroup of the group of isometry groups on Rn that fixes a set of point x as a subset of Rn. It is important to realize that the symmetry group of x depends both on r to the n and on x. For example, the symmetry group of the origin in R1 is z mod 2, because it must be something that flips about the horizontal axis, but the symmetry group of the origin in R squared is the entirety of O2. Theorem 12.15. The only finite symmetry groups in R squared are z mod n or d sub n. Proof. We simply need to find all the finite subgroups G of E2. Any finite symmetry group G in R squared must fix the origin and must be a finite subgroup of O2, since translations and glide reflections have infinite order. By example 12.10, elements in O2 are either rotations of the form r theta is equal to cosine of theta negative sine theta cosine theta, or reflections in the form t of theta is equal to cosine t of phi is equal to cosine of phi negative sine of phi cosine phi times 1 0 0 negative 1. Notice that the determinant of r theta is equal to 1, the determinant of t theta is equal to t phi is equal to negative 1, and I think what it wants to say is that the order of t, the determinant of t phi squared is equal to I. Isn't necessarily the case that t phi squared is equal to I? It doesn't look like it, but we're just going to go with it for now. We can divide the proof up into two cases. In the first case, all of the elements of in G have determinant 1. In the second case, there exists at least one element in G with determinant negative 1. Case 1. The determinant of every element in G is 1. In this case, every element in G must be a rotation. Since G is finite, there is some smallest angle, say theta naught, such that the corresponding element r theta naught is the smallest rotation in the positive direction. We claim that r theta naught generates G. If not, then for some If not, then for some positive integer n, there is an angle theta 1 between n theta 0 and n plus 1 theta naught. If so, then n plus 1 theta naught minus theta 1 corresponds to a rotation smaller than theta naught, which contradicts the minimality of theta naught. Case 2. The group G contains a reflection T. The kernel of the homomorphism phi G goes to negative 1, 1, given by A goes to the determinant of A, consists of the element whose determinant is 1. Therefore, the order of G divided by the kernel of phi is equal to 2. We know that the kernel is cyclic by the first case and is a subgroup G of, say, order n. Hence, the order of G is equal to 2n. The elements of G are r theta all the way to r theta n minus 1, t r theta all the way to t r theta n minus 1. These elements satisfy the relation t r theta t is equal to r theta to negative 1. Consequently, G must be isomorphic to d sub n in this case. That's actually a fairly clean proof, okay. The wallpaper groups. Suppose that we wish to study wallpaper patterns in the plane, or crystals in 3 dimensions, particularly of use to like chemistry, either physicists who work with chemistry or just like regular chemists who work in chemistry. Wallpaper patterns are simply repeating patterns in the plane, as we can see in figure 12.16. The analogs of wallpaper patterns in R3 are crystals, which we can think of as repeating patterns of molecules in 3 dimensions, which we can see in figure 12.17. The mathematical equivalent of a wallpaper pattern or a crystal pattern is called a lattice. Let us examine wallpaper's patterns in the plane a little more closely. Suppose that x and y are linearly independent vectors in R squared. That is, one vector cannot be a scalar multiple of the other. A lattice of x and y is a set of all linear combinations mx plus ny, where m and n are integers. The vectors x and y are said to be a base for the lattice. Notice that a lattice can have several bases. For example, the vectors 1, 1 transpose and 2, 0 transpose have the same lattice as the vectors negative 1, 1 transpose and negative 1, negative 1 transpose. However, any lattice is completely determined by a basis. Given two bases for the same lattice, say x1, x2 and y1, y2, we can write y1 is equal to alpha 1, x1 plus alpha 2, x2, with y2 is equal to beta 1, x1 plus beta 2, x2, where a1, alpha 1, alpha 2, beta 1, and beta 2 are integers. The matrix corresponding to this transformation is U equals alpha 1, alpha 2, beta 1, beta 2. If we wish to give x and y, x1 and y, x2 in terms of y1 and y2, we need only calculate the inverse of U. That is, u to the negative 1 of y1, y2 is equal to x1, x2. Since u has integer entries, u to the negative 1 must also have integer entries. Hence the determinant of both u and u to the negative 1 must be integers. Because u to the negative 1 is equal to I, determinant of u to the negative 1, equals determinant of u to the negative 1 equals I, and consequently, the determinant of u is of either plus or minus 1. A matrix with determinant plus or minus 1 and integer entries is called unimodular. That is a term. I don't know if the term was originally coined in number theory or was coined in a more general context, but unimodular matrices are fairly important, especially when you start doing a lot of matrix manipulation stuff, because a bunch of stuff corresponds in terms of modularity to a bunch of other stuff. For example, the matrix 3, 1, 5, 2 is unimodular. It should be clear that there is a minimum length for vectors in a lattice. We can classify lattices by studying their symmetry groups. The symmetry group of a lattice is a subgroup of V2 that maps the lattice to itself. We consider two lattices in R² to be equivalent if they have the same symmetry group. Similarly, oh gosh, give me a second, my throat is having a moment. Alright, that's better. Similarly, classification of crystals in R3 is accomplished by associating a symmetry group, called a space group, with each type of crystal. Two lattices are considered different if their space groups are not the same. The natural question now arises is how many space groups exist. A space group is composed of two parts, a translation subgroup and a point. The translation subgroup is an infinite abelian subgroup of the space group made up of the translational symmetries of the crystal. The point group is a finite group consisting of rotations and reflections of the crystal about a point. More specifically, a space group is a subgroup of G as a subset of E2, whose translations are a set of the form I, T, or T and L, where L is the lattice. Space groups are, of course, infinite. Using geometric arguments, we can prove the following theorem, which we can see reference 5 or 6 for a complete proof. Theorem 12.19. Every translation group in R² is isomorphic to Z times Z. The point group of G is G0 is equal to A with A, B in G for some B. In particular, G0 must be a subgroup of O2. Suppose that X is a vector in a lattice L with space group G, translation group H, and a point group G0. For any elements A, Y, and G, AY, IX, AY to the negative 1 is equal to A, AX plus Y, A to the negative 1, negative A to the negative 1Y is equal to A to the negative 1, negative A to the negative 1Y plus AX plus Y, which is all equal to I, AX. Hence, I, AX is a translation group of G, is in the translation group of G, by normality. More specifically, AX must be in the lattice L. It is important to note that G0 is not usually a subgroup of the space group G. However, if T is a translation subgroup of G, then G over the translation group is isomorphic to the point group. The proof of the following theorem can be found in 2, 5, or 6. Theorem 12.20. The point group in the wallpaper group is isomorphic to C sub n or D sub n, where n is equal to 1, 2, 3, 4, or 6. To answer the question of how many point groups in the translation groups can be combined, we must look at the different types of lattices. Lattices can be classified by the structure of a single lattice cell. The possible cell shapes are parallelogram, rectangular, square, rhombic, and hexagonal. The wallpaper groups can now be classified according to the type of reflections that occur in each group. These are ordinary reflections, glide reflections, both, or none. So we have 4 examples here of like what such a thing would be. So we have the 17 wallpaper groups. Note for the notation for space groups: P1, P2, P3, P4, all the way up to P6, PM, PG, CM, PMM, PMM, PMG, P2G, C2MM, P3M1, P31M, P4M, P4G, and P46. And we have all these different types of lattice, all these different lattice types, and what type of reflections they have. Theorem 12.33. By previous research, they're not proving this here. There are exactly 17 wallpaper groups. The 17 wallpaper groups are listed in table 12.22. The groups P3M1 and P31M can be distinguished by whether or not all their threshold centers, their threefold centers, lie on the reflection axes. Those of P3M1 must, whereas those of P31M may not. Similarly, the fourfold centers of P4M must lie on the reflection axis, whereas those of P4G need not. The complete proof of this theorem can be found in several of the references at the end of this chapter, including 5, 6, 10, and 11. Oh wow, even they're saying that Sage is useless in this chapter. Nice. Historical note. Symmetry groups have intrigued mathematicians for a long time. Leonardo da Vinci was probably the first person to know all the point groups. At the International Congress of Mathematicians in 1900, David Hilbert gave a now famous address outlining 23 problems to guide mathematics in the 20th century. Hilbert's 18th problem asked whether or not crystallographic groups in n dimensions were always finite. In 1910, L. Beiberbach proved that crystallographic groups are finite in every dimension. Finding out how many of these groups there are in each dimension is another matter. In R cubed, there are 230 different space groups. In R to the 4th, there are 4,783. No one has been able to compute the number of space groups for R to the 5 and beyond. It is interesting to note that crystallographic groups were found mathematically for R cubed before the 230 different types of crystals were actually discovered in nature. So, what is a non-singular matrix? Give an example of a non-singular matrix. So a non-singular matrix is an invertible matrix. The simplest type of non-singular matrix is this, with identity itself. Alright, what is an isometry in R to the n? Can you give an example of an isometry in R squared? So an isometry in just generally any metric space, I'll use some topology terminology. So an isometry is a map that preserves distances between vectors, or distances between objects. What is an orthonormal set of vectors? An orthonormal set of vectors is a set of vectors that are orthogonal, and they span the space. And they all have length 1. What is the difference between the orthogonal group and the special orthogonal group? So orthogonal group is the set of all determinant plus, well, not the set of all determinant plus minus 1 matrices, but the set of all matrices such that their transpose is equal to the identity. So we have A is an O to the n if A to the negative 1 equals A transpose. And the special orthogonal group restricts that to matrices of determinant 1. And what is a lattice? A lattice is a collection of points, or you could draw them as lines, generated by linearly independent vectors and their additions with m and n. Okay, so the lattice xy for linearly independent, I should note, linearly independent is equal to the set of all mx plus ny for all n integers, positive or negative. So basically, these patterns of lines are linearly independent that tile the plane in R2. Okay, man. I'm probably going to do only some of these, because this is not specifically something that interests me. And it's kind of unfortunate that a lot of these more so have to do with geometric applications and like chemistry-based, physics-based applications. These references are a lot of like things that are deep into it that are more interesting in it, but I'll try to do some of the proof-based questions. Before that though, your regularly scheduled intermission. Okay, I just chugged the whole town's worth of water. Let's get these exercises done. Okay, switch back to proper scene, standard textbook scene. Alright, prove the identity xy equals 1/2 x plus y squared minus x squared minus y squared. How does it want me to do this? Okay. So the length of x and y is equal to, alright, so the length of x, difference between x and y. Let me quick double check how they actually wanted this properly done. Oh wait, no, never mind, I actually don't need to even know that. I think instead, you need to note the fact this is equal to 1/2. Oh well, I should probably write it out in a better way. So, it's the absolute value of x minus y, right? Or no, x plus y squared minus x squared. X squared minus y squared. This is going to be plus y, x plus y, minus x, x, minus y. Let me double check. This is what it is, right? So it's going to be x1. It's going to be x1 plus y1 squared plus all the way up to plus xn plus yn squared minus x1 squared minus minus x to the n squared minus y1 squared minus minus y to the n squared. So from here, notice that x1 plus y1 squared is equal to x1 squared plus 2xy, 2x1 y1 plus y1 squared. So we can rewrite this sum, because we have a finite number of terms, as x1 squared plus 2x1 y1 plus y1 squared minus x1 squared minus y1 squared plus on and on to, oh gosh, I might have to actually move this up. Or actually, I'll just like, I'll scrunch this part of the board. Whap. We take this, move it up here. Plus xn squared plus 2xn yn plus yn squared, minus xn squared minus yn squared, which all these cancel out. These squares and these cancel out. So we have like all this cancellation, and from this we get a remainder of 2 x1 y1 plus x2 y2 plus plus xn yn, which is equal to 2 inner product of x, y, which is like it's the same as what we wanted to prove, except that we multiplied this by 2, but we also multiplied what we wanted to prove by 2, so it all cancels out. Alright, so show that L1 is a group. So we have, first of all, orthogonal group. Since A transpose is equal to A, we have that if A is an O of n, A to the negative 1 equals A transpose is an O to the n. We have that 1, 0, 0, 1 is an O to the n. And we already have associativity predefined. So all we need to show is that A, B, if we have two matrices AB, AB transpose is going to be equal to, I'm trying to remember how it goes. I don't know if it's A transpose B transpose or B transpose A transpose. So like, let's think. This sends so let's notice that, okay. Each term in this is going to be Cij is going to be the sum from I for our initial row. Oh gosh, let me think. So we sum I equals 0 to n of A, I, so, oh no, I think it will be, oh, I should probably use a different running index. So k equals 1 to n. So we sum A, I, k, we're just changing the column by B, K, J, right? So Cji is equal to the sum from k equals 1 to n of A, Jk, B, Ki. So its transpose is going to be equal to that. How do we think of that in terms of A and B? Well, let's guess we replace I with J, which is what we normally would have done anyway, so I'm pretty sure is going to be equal to A transpose B transpose. So yeah, AB transpose is equal to A transpose B transpose, or the, so yeah, so we can then form its inverse by BA. Form its AB where it's transpose its own inverse. Oh wait, no, I'm being dumb, yeah. It would be B transpose A transpose, because we're swapping the I's and J's around. So actually doing that math with the transpose would like swap these around. But B transpose A transpose times AB is going to be equal to ID. Which shows that this is closed, that the product of two orthogonal matrices is going to be orthogonal. Which shows what we need. Nice. Prove the following matrices are orthogonal. Man. Nash. Determine the symmetry group of each of the figures is figure 15.25. Hey. I'm not interested in a lot of these like pictographic kind of application-esque things. I'm more interested in like these type of things, like verifying things are a group. I'm talking about bases for lattices, or things like semi-direct products of groups. Semi-direct product of groups. So 5. Let x, y, and w be vectors in R and N, and alpha in R. Prove each of the following propositions to the inner product. So okay, I'm gonna take symmetry as a given, because in this case it's mainly that we just swap around the indices. All right, x, y plus w is equal to x, y plus x, w. So x plus x, y plus w. Yeah, so x1, y1. So, okay, actually, wait. Let me write it in better sum notation. That makes it way easier. X, y plus w is equal to the sum of xi, yi plus wi is equal to the sum from xi, yi plus xi, wi is equal to the sum of xi, yi plus the sum from xi, wi, which is equal to xy plus xw, which refers to something called bilinearity, which are important for certain types of transformations, but I'll just leave it at that for now. Alright, alpha x y is equal to, this should be obvious because you can distribute it between the entire product, so I'm going to take that as given as well. Gosh. Yeah, this is also like really simple, because if any, yeah, the only subtle thing is that the absolute value of x equals the sum of xi, and important here to note, squared. Now this square means that if any value, any coordinate of x is non-negative, its length is going to be, or this inner product is going to be non-negative, or non-zero. Then any length is, then any term of this is going to be non-zero, and the sum of positive terms is positive. So we know that we only have equality when x equals 0 and everything is 0. And then from here, because xx is equal to, yeah, if xx is equal to, xx is greater than or equal to 0, in this case, we have x possibly not being 0. So we know that if y is not equal to 0, then y is not equal to 0. This is falsified, which means that y must be equal to 0 for this to hold. Alright, verify that en equals ax, a and O of n, and x and Rn is a group. Alright, so because A is an O of n, we know that we have that inverse AT we know we have that inverse in there, and we also have the identity in there. So we just need to show that any two matrices of this form hold. Okay, closure is actually obvious for E of n. So how do they define it? Yeah, because it's like kind of like a non-abelian thing. So we have A x times b y is equal to ab. A x, was it minus or plus y? Let me double check. Where did they define the Euclidean group? Because Euclidean group always confuses me. Yeah. Oh wait, actually, yeah. So ay plus x. Oh, so actually what we need to show is we've actually shown everything besides associativity. So let me quick do that with the Euclidean group. So C of Z is going to be equal to AB. AY, is it AY plus X or AY minus X? AY plus X, okay. AY plus X. C, Z is equal to A, B, C. A, B, Z plus AY plus X, which this is equal to A, B, C, A of BC plus Y by linearity plus X, which means that we can pull out this X to get A, let's quick also, to get A, excuse me, to get A X multiplied by BC BZ plus Y, which is just equal to A of X multiplied by B of Y multiplied by C of Z, which shows that we have associativity. We do have a group structure on E to the n, or even. Alright, so going back, scrolling back down. We have, okay, we verify that the Euclidean group is a group. I'll let G be a subgroup of A2 and suppose that T is translation. T is translation. G. G over T. Again, like translation groups just ain't really my jam here. And especially, I know the rest of the book. The rest of this book doesn't really go into this. So I'm like, why should I? Like, group actions always have an applicable use. I know that in algebraic topology and differential geometry, but I don't really see this group being used in the pure, like in a pure geometric setting, or those settings where they are used. I'm not really interested in. Alright, AS2, let's put all x, y, 2 sets of parallelogram, r squared. Same as parallelogram with sides AX and AY. Okay. I don't know. So it has determinant of 1, so it scales areas by 1. I'm just trying to think of, like, in what respect? In what respect would you prove this? I mean, like, I'm just trying to, I'm wondering what level of rigor they want for this. That's the main thing I'm confused by. For this, it fundamentally comes down to the fact that this is determinant 1 because it's in special linear. In fact, you can just have it be the, like, plus minus 1 matrices and it would still work. So, our determinant matrices. So yeah, a lot of this is literally just like, this preserves area. AX and AY is the parallelogram, the area of the parallelogram, and XY is transformed into that, yeah. I don't know what it specifically wants me to prove there, or how they want me to prove it, so I'm just going to skip that for now, before I make a fool of myself. Alright, prove that SON is a normal subgroup of O of N. Oh, this is actually simple to show. So suppose that determinant of A equals -1. So we have a member of O of N that's not an S of O n, right? Well, A, B, A to the -1, determinant of this is equal to the determinant of A, determinant of A to the -1, determinant of B. Because the determinants, like, they're numbers, they like commute scalarwise, which shows that this is just equal to a matrix of determinant B. I wonder if this actually then applies for the entirety of GLN. Because of this determinant multiplication property and the fact that we're like taking a homomorphism to an abelian group, I wonder if this shows that like O of N is actually normal in GL2 of N. Because the determinant of A to -1 is defined for all GLN of R. Huh. Cool. Alright. Proof it is proven L1 E2 of the form X has infinite order. I feel like it wouldn't. Yeah, because like, think of the matrix 0, which actually, let's think about how I want to write this. It sends A, it's going to send A to -1, 0, and it's to 0, -1. And let's consider the matrix 1, 0 under this A, which this is just equal to -1, 0, right? So A, 1, 0, A, 1, 0 is going to be equal to A squared 1, 0 minus 1, 0 is going to be equal to A squared 0. Then multiplying this by A 1, 0 gets us A cubed 1, 0 again. Oh, wait, actually, let me not be hasty while thinking about this. Let me go back to remind myself of the actual structure we had, because the structure we had is a bit sneakier. Yeah, okay. Well, in this case, we can modify it to like make it somewhat nicer. So instead, we have A squared on this side, and we multiply A squared by this. Actually, oh wait, no, yeah, never mind. Because we have A squared, I'm being me again. Don't worry about it. Oh god, no, I'm covering up that part of this thing I have. Okay. So because A squared is just the identity matrix, we're going to be having A cubed equal to A along with 1, 0. So we found a matrix, an element of the Euclidean group with order 3. Or actually in this case it'd be order 2. But when you have 3 permutation, it comes back around to your first initial thing. So we found an element of E of n with order 2. So no, not every element of E of n has infinite order, even when x is not equal to 0. Oh, show that any isometry of f is a 1-to-1 map. Easy. So if f of x equals f of y, then f of x minus f of y is equal to 0 is equal to f(x) equals the absolute value of x minus y, which is only equal to 0 if y is equal to x. So for this to be true, we know that y must equal x, so the map is 1-to-1. There exists an infinite abelian subgroup of O of n. I mean, what I'm thinking for an infinite abelian subgroup of O of n is that we define a element cosine. We define an element cosine of n, cos of n, negative sine of n, n, and we talk about all the matrices generated by this, or we could say cosine 1, negative sine 1, sine 1. And the reason that this will be infinite, first of all, it's abelian because it's cyclic, but it's infinite because we don't have an irrational angle. So we have an angle that will never have a multiple that equals pi or 2 pi. So we'll never go back around to n. More specifically, if you wanted to get a bit more a bit less anty with it, you can define 2 pi over n, 2 pi over k, or actually, so we can define 2 pi e, right? E will never be, whenever you multiply it a certain number of times, will never be an integer. As such, 2 pi e is never going to be an integer, or it will never produce the same output of under either cosine or sine twice, which means that this group will be infinite, and because it's cyclic, will be abelian. So yes, O of n contains a infinite abelian subgroup. Is an of 2, show that x is also a point of the unit circle. It's probably going to be a cosine or sine argument, so that's geometric zone A. Alright, 15. Let G be a group with a subgroup H, which is not necessarily normal, and a normal subgroup N. Then G is a semi-direct product of N by H, if H intersected with N is the identity, and Hn is equal to G. Show that the following is true. S3 is a semi-direct product of A3 by H equals 1, 1, 2. The quaternion group Q8 cannot be written as a semi-direct product. And E2 is the semi-direct product of O2 by H, where H consists of all translations in O2. I'm not going to be worrying about the quaternionic group. S3, they should be easy if I just what the permutation group is. So, first of all translations, any translation, is not linear, so it's not an O2. So from here, E2, so okay. Suppose we have some AX. We want to show it's the semi-direct product of A0 and I of x. Oh, for some x. Oh, wait, no. Wait, actually, we can show that by just showing a to the negative 1 x. So this is going to be equal to a to the negative 1 x equals a x. And because it's in the orthogonal group, it's going to be invertible, so this element exists, so that's true. And this is the set of all rotations, or all translations. This is the set of all rotations. Nice, and translations. That's pretty much it. Oh gosh, I just saw this crystallography and cohomology of groups. Yeah, this is a short stream, but I kind of wanted it to be a short stream because I really don't enjoy this topic compared to a lot of the other like theoretic abstract topics in abstract algebra. So I'm probably going to spend my time reading this because I'm painfully interested in what this is about, because this is like cohomology. I normally don't hear it associated with groups, but I'm very interested. Okay, I know cohomology is related to groups. Like, groups are literally your cohomology and homology objects. But, like, I'm talking about when, like, in the context of groups instead of spaces. So, I will probably be reading that for a bit, and I might come back on, because this next chapter, the structure of groups, this chapter is some good stuff, I'll just say that. So, until then, yeah, I'll just keep the stream short, like, less than 2 hours, thank God. So, not see ya. What am I doing? Alright, thanks for tuning in. Have a nice